so we today are going to be looking at predicting redox reactions. So given a whole bunch of species in solution, if I add a whole bunch of things together, what two things are most likely to react? And so I have a little space there in your notes for you to write down the steps, and then once we write down the steps, we'll go look at how we would write out our half reactions and predict our reactions from there. So the first thing you need to do is list all the species present. And so when you do this, you need to make sure you're doing some specific things when you write. So when they give you the reactants, you have to write out what's there. Now when you do this, you kind of need to follow some rules. Soluble ionic compounds as well as acids will dissociate. You would have learned this last year in Chem 20, right? If I put salt in water, it breaks into sodium and chlorine. If I put an acid in water, we say it breaks apart into hydrogen atoms and whatever the anion is. So we need to include that. Molecular compounds, we do not dissociate. So remember, if I take sugar and I put it in water, although sugar dissolves in water, it does not dissociate. So it technically would just stay as C6H12O6 aqueous. If it's in an acidic environment, you're going to include H2+, right? So this would stay like C6H12O6 would just stay as like aqueous. If they dissociate, you'd write them into their ions, aqueous and Cl, for example. There's a few people gone. And you always also need to include water. Water is present in these reactions, or these reactions are happening in water. And water can also act as a SOA, as an oxidizing agent and as a reducing agent. Like, water can help in the facilitation of, like, rusting happening, right? So, water is, you need to count water as part of your reactants. So that's the first thing you're going to do if you're going to have to predict redox, is write out everything that there is. Okay, the next one is you need to identify each substance as an OA or an RA. Would they lose electrons or would they gain electrons? And so you'd say OA, RA for every single species. Could they act as an OA? Could they act as an RA? We also have 4 species here that act as both OAs and RAs. So then rather than, looking for them on the chart, if you just remember them, it makes your life a little bit easier. And Mr. Shelley had a saying that says, feel hot. Good for him for making that up. If you Google it, it does not come up on Google. Alright, so feel hot, creamy solid. So Fe, F for iron, H for water, C for chromium, Sn for snot. So it acts as, those guys act as both OAs and RAs. Okay. Once you've written out which is OAs, which is RAs, you have to identify which of all of those compounds or ions that are in there, which of them is the strongest oxidizing agent, which of them is the strongest reducing agent. Once you find that out, obviously, those will be the 2 that react. Essentially ignoring the rest as spectator ions, yeah. And so you use your data booklet to identify which is the strongest, which is the weakest. We're assuming that, these reactions are occurring under the conditions that the data booklet has described. Once you're done that, you have the SOA, the SRA. You'll write out the redox half reactions. The reactions are right on that table for you. You can literally just copy them out. Just copy these from table. But make sure you're putting them in the right order, right? These are all on the table are reduction half reactions. You need to make sure if it's the one being losing electrons, or if it's the RA, that you flip that equation around. Once you've done that, you need to determine the net ionic reaction. Make sure that your E negatives are balanced, right? We have to have the same number of electrons transferring from your RA to your OA. Or OA, yeah. RA to OA, yeah. Mm-hmm. That's what you guys did for redox? Okay. Yep. Yep. Oh, okay. Okay. And then the last thing you need to do is determine spontaneity. Just because you have like something as the strong OA and the strong RA doesn't necessarily mean that they are going to automatically spontaneously react. You still have to say whether that reaction would be spontaneous or non-spontaneous. You can always make a reaction occur, but in these natural, under the conditions on the data booklet, these reactions may not occur naturally. Whew, what's going on that side? There's a lot there. Rules for determining aqueous solutions contain water, acidic solutions contain hydrogen, basic solutions contain OHs. I don't think you need to write all this down. So the strongest OA, so from all of this, what we're doing is we're taking that the strongest OA and the strongest RA, ignore that, will react. Everything else we ignore as a spectator ion. So it's kind of just building off of what you look in Chem 20 for spectator, for net ionic equations. And so just as a note that kind of might help you figure out like what's the SOA, what's the SRA, rather than, you know, kind of sort through your chart every single time, is the most reactive metal tends to gain electrons, and they are the strongest OA. The least reactive metals tend to lose electrons and are the weak OA. Weakest OAs are the what for RAs? SRAs. So just, if you're copying down your notes there, just what I underlined. Right, so let's look at, just kind of putting these steps into practice and some reactions. So, predict the most likely redox reaction when chromium is placed into aqueous zinc sulfate. So, chromium, I'm gonna just first of all write everything out that I have here. So, chromium, Cr, it's just like a piece of metal I'm putting in there, so it's chromium solid. The next one, aqueous zinc sulfate. And so this is an ionic compound. I would go look on the solubility table, or just assume it's aqueous, so therefore it has dissociated into its ions. Zinc is a 2+ aqueous ion, and sulfate is a SO4 2- aqueous. The other thing that I need to always include is water. H2O as a liquid. So I wrote out everything there. SO4 is 2-, yep. Alright, so chromium solid, zinc 2+, SO4 2-, and water. So there's 4 things in this solution. So then I'm going to go consult my table. And I'm going to look to see, okay, chromium, pardon me, that would be a chromium ion is both. Chromium solid is just going to be down here, so it's a Ra. Pardon me? So iron, feel hot, water, creamy, chromium, snot, tin. Those are all the ions, not the metal form. Yeah. Can I help you? We're live right now. We're live. Chromium is a Ra. Then I go look for my zinc 2+ ion. Zinc 2+ is a OA, if I go find it on here. So this is a OA. I'll go look for the sulfate ion. The sulfate ion by itself does not react, but it will react with water. If you look up here, it's actually quite a strong, it's right kind of towards the middle of your chart. It is actually quite a strong OA when those react together. And then water is both a OA and an RA. So I gotta go say, what's an OA, what's an RA for every single thing here. And then what I need to go do is figure out of everything that is an OA and everything that is an RA, which is the strongest. So my 2 options for the OAs are the zinc and the reaction between sulfate and water. And so if you look higher up on the left is the zinc half reaction. It's right here. Well, the sulfate is right here. And so this would be the SOA. And between water and chromium, the stronger reducing agent is chromium. So that's my SRA. So now that I've figured out what's my strongest OA and what's my strongest RA, I'm then going to go write the half reactions for each of these. So zinc 2+, and because zinc is the OA, it's being reduced, I can just write the exact half reaction that appears on this table. So zinc plus 2 electrons is going to become zinc solid. That's this one. That was my SOA. The next part, then I'd have to write the half reaction for the chromium solid. Now, when I'm writing this down, make sure that you're writing the chromium reaction going this way, because that's the reducing agent, so it's the loss of electrons. Can you rephrase the question? So chromium is going to become Cr2 positive plus 2 electrons, just based off of that half reaction on the table. Sorry, can you rephrase your question? Right, but I mean, there is no PbO2 in here, so I couldn't have that as a half reaction. Right, it has to be exactly what they're telling me. Okay? And so the last thing I need to do is just summarize here and say, okay, well, what is the net redox reaction? As long as the electrons are balanced on the reactants and the products, I'm just summarizing this similar to what we have done previously. So the zinc ions, sorry, I should put aqueous. Zinc has a 2+ aqueous charge, is reacting with chromium solid to produce chromium 2+ aqueous ions, and zinc solid. And that is my reaction. The last thing I would need to do is go determine spontaneity. And so, where's zinc? Where are you at, zinc? Zinc is right here. The reaction for chromium is below it right here. So zinc, the reaction between zinc and chromium, my OA is above my RA. So right over top of my arrow, I'll just say spontaneous. Yes. If we're doing this and then it's not, you say non-spontaneous because we can make that reaction occur. It just requires an input of energy. Mm-hmm. You will still tell us what happens. Before, when we were doing those half reactions, we were just like, oh, we don't know what happens. But now we can say what happens. I don't, well, I'm not sure. I don't know. I'm not sure. I know what you mean. All right, another question. I'll do one. You do one? One more. All right, so predict the most likely redox reaction when potassium permanganate is slowly poured into acidic iron 2 sulfate solution. So the first step I need to do to determine what redox reaction is going to happen here is going to be to write everything out. So potassium permanganate, that's aqueous, so it would break apart into its ions. So potassium, K+, aqueous. Permanganate is the MnO4 negative aqueous ion. Is slowly poured into acidic. As soon as I see acidic, what do I have to add as part of my list? H's, right? Aqueous. Iron 2, that's telling me the charge on iron when it dissociates, so it's Fe2 aqueous. Sulfate, SO4 2 negative aqueous. And lastly, these are occurring in solution, so I need to add water. Does everybody understand how I'm breaking that apart? I will always break them into their ions, right? These are all aqueous, so you have to break them apart into their ions. Unless it's just a chunk of metal, and then it stays a metal. That is aqueous. They would all be aqueous, right? H2O is liquid. They're all occurring in water, and water can have a gain or loss of electrons, so we have to add it as part of our OAs and RAs. We are always assuming these reactions are occurring in water. Alright, so then the next one I gotta go say, list all of which are OAs, all of which are RAs. So if I go consult my table here, potassium, it's on the left-handed side, so this is a OA. I always put OAs above and RAs below, whatever makes sense for you. The reaction, if you check on here, the reaction between permanganate, MnO4, reacts with hydrogen. That's actually a super strong oxidizing agent right towards the top of your chart. And so these two can react in an OA. Probably going to be my SOA, but let's not count anything out. Then I go to the iron 2+ ions. That's part of my fuel hog creamy snot. That's the Fe2+ ion. So this is both an OA and an RA. Sorry. Good? What's your question? If it's iron 3+, it can only be reduced to iron Fe2. Reduced, yeah, gained electron, right? But Fe2 could go to Fe3+, or can go to Fe solid. That's why it has both of them. If it's iron 3, you could only be the gaining of electrons. There's the reaction between sulfate and water. So this is a OA. And last of all, water is both an OA and an RA. So once I figure out what's my OAs, what's my RAs, I'd appreciate if you weren't talking while I'm trying to think. Yeah, Amy. Why is hydrogen what? H is hot. H is for water. H2O, water. No. Okay, so once I list all my OAs and RAs, I go check out all my OAs. This this permanganate hydrogen reaction is super high up. There's nothing higher than that. So this is going to be my SOA, is the reaction between these two. And then I'm going to look between the iron ion, the iron 2+ ion, and the water to determine my RA. And if I look, the iron is actually going to be my SRA. So then I will go write both of those reactions out. We'll have to balance them out. Sorry, can you see that? I'll just do green. So MnO4 negative. So this is the oxidation reaction. So I can write out this reduction half reaction. So it's MnO4 negative aqueous is reacting with 8 hydrogen ions. This is just from your table, right? I'm just exactly writing this equation out. Plus 5 electrons is producing, sorry, just let me finish. Mn2+ aqueous and 4 H2O liquids. Sorry, what's your question? It's the reaction between MnO4 and hydrogen. Both of these guys react together to give your SOA. Yes. Yeah, if you look on here, there's no just MnO4 reaction. It has to be MnO4 with hydrogen. Yeah. So that's my first, is that the oxidation or reduction reaction? It is my reduction reaction because the electrons are on the left. The next thing I need to do is go write the half reaction for my RA, or my loss of electrons. So I would go look for the half reaction for when the tin ion is on the right-hand side. So that's way up here. So Fe2+. And so make sure that you're writing the reaction going this way now, right? I'm writing it as the loss of electrons, not the reduction reaction, which is what this is representing if I go from right to left. So Fe2+ is creating Fe3 positive and 1 electron. And so to write my net redox reaction, I need the electrons to be balanced. So this first reaction, there's 5 electrons, and here there's 1. So what would I have to do? I would take the second reaction, yeah, and times it by 5. And so that would change this to 5, this to 5, and this to 5. And now I have a balanced transferring of electrons from RA to OA. And so then I can summarize my reaction. So essentially what's happening is that manganese ions, aqueous, are reacting with 8 hydrogen ions, aqueous, and the tin 2+ ions, aqueous, to produce, sorry, I should have the 5 there, thank you. And 5 Fe3 positive aqueous, producing permanganate ions, MnO2 aqueous, and water, 4 H2O liquids. And then the very last thing I would need to do is determine spontaneity. Well, that permanganate and hydrogen ion reaction, the OA is super high, and iron 2 as that reduction, or as the RA, pardon me. OA is higher than RA, so that would be spontaneous. That is a 4. Yeah, just copied right from up there. Because I need them. It wouldn't be balanced otherwise. That is part of that. That's part of the permanganate half reaction. Okay, so take a minute here, and I want you to do number 3, YT number 3. Predict the most likely redox reaction when silver is placed into aqueous cadmium nitrate. So try this. That says YT1 on there. On my notes it says 3. So try that for a second. So write everything out and then figure out what's the OA, what's the RA, and write your net redox reaction. Oh, predict the most likely redox reaction when silver is placed into aqueous cadmium nitrate. So silver is Ag solid. Aqueous cadmium nitrate, if you look, and that's ionic, right? So I need to break it apart with its charges. These cadmium 2 plus aqueous. Nitrate is NO3 negative aqueous. And I always need to include water. Once I'm done that, then I just go and say, what's the OAs, what's all the possible OAs, what's the possible RAs. If you look at this, silver is only an RA, cadmium is only an OA, nitrate, it can only react if it reacts with something else. So right now, if nitrate is by itself, or it's with something else, it's a spectator, can't act as an OA or an RA. And then the last one is water, OA and RA. So then you go consult your chart to see which one is a higher OA and a lower RA. Sorry, Austin, go ahead. Why is Ag not an ion? Because it's silver. It's just saying a solid piece of silver gets dropped in there. I know I put it in water, but is it going to react? I don't know. Right now, before I react it, it's just a solid piece of silver. Because this is aqueous, and so you break it into its ions. If it's an aqueous ionic compound, it will break. If it's soluble, it will break apart. If it's just a piece of metal or something, it's just rated as solid. If it says aqueous what, sorry? But silver can't be aqueous by itself. It has to already be part of something else to disassociate. Yeah. Yeah, when silver is placed, well, it's just got to be a chunk of silver, right? It would tell you aqueous if it was, yes. Okay, so once I do this, then I go look, so figuring out my OAs. If I look when water is in OA, it's right down here. And what's my other OA? Cadmium is an OA, it's just slightly above it. So that's going to be my SOA, and I could write that half reaction, Cd2 plus 2 electrons. Is reacting to produce cadmium solid. And I write that reaction because it is an OA. It is the the reduction half reaction that I'm writing out. And that's also what I start with, Cd2+, so it has to proceed from there. The next one then is the SRA. So I have water. When water is an SRA, it's quite high, it's up here, and silver is just below it, solid when it's a solid form. So that would be my SRA, and so I'll write that half reaction. Silver solid, so that's again what I'm starting with, and I have to be proceeding to the left because it's a loss of electrons. So I'm starting from silver solid and going to silver positive, which has 1 electron. And so if I'm writing my net redox reaction here, I need to balance this in terms of electrons. So I need to take this and times it by 2. So that would go to 2, 2, and 2, and so the electrons cancel each other out. And then I just summarize my reactants and products. So cadmium 2 plus aqueous is reacting with 2 silver solids to produce 2 silver aqueuses and a cadmium solid. The last thing you should do is predict spontaneity. And cadmium is there and silver is there, so non-spontaneous. Okay. All right. So, sorry. Where did I go? Yeah, sorry. I'm just gonna write down homework and then I'll go back. So the homework that you guys are looking at, it's not gonna be everything from homework. What is it? 4 we're on. All right. So homework 4, you're gonna look at numbers Just number 1. Just number 1. 1 A to G. So homework 1. So homework 4. Questions number 1 A to G. Please, if you're having problems, let me know.